Hello everyone, it is a great pleasure for me to be presenting this talk at AICHE this year, even though it is not in person. So I am Professor Bruno Blais, but the work I will be presenting today was in large part carried out by a master student of mine that I co-directed with Professor Fradette and Professor Bertrand, whose name is Bastien Delacroix. So today we'll be discussing on the comparison of the performance of mixing systems for viscous solid liquid mixing using CFD-DEM. So when we discuss solid liquid mixing, one of the key industrial requirements is characterized by the state of the suspension. So either we can be in partial suspension, in which the majority of the particle, or at least a large fraction of them, will remain at the bottom of the vessel. At the opposite end, we can be in homogeneous suspension, where the concentration of solid is pretty much homogeneous throughout the vessel. And in between, we have the state of complete suspension, where the particles are all suspended from the bottom of the vessel, but they're not necessarily homogeneously distributed within the vessel. This is generally where we want to operate at for some chemical processes, because it guarantees maximal contact area between the two phases, so the solid and the liquid. So you can imagine, for example, if the solid is a catalyst, then you have a maximal mass transfer between the two phases. And the speed at which this is reached, so the impeller velocity for which you reach complete suspension, is called NGS, which is generally estimated by correlations. So there are some key issues related to NGS. NGS is notably hard to estimate, and thus far the work has mostly focused on the turbulent regime of operation. And it's really unclear what is the role of the fluid and the particle properties. If you look at the present state of the art, right now the majority of let's say the information used to estimate NGS is in the form of correlations, in which you have a very weird exponent such as 0.45, which always make me a bit, let's say, wary of the results that we will obtain. So right now the approach is really limited to correlations. They're mostly empirical or semi-empirical, such as the Zwittering correlation. And the issue is that these correlations, they all encompass the geometry within a certain parameter, which is generally, let's say, in the case of the Zwittering correlation, coined S. So the issue is S encompasses the entire geometry. But when we're looking at laminar solid liquid mixing, we're looking at a very large range of geometries which we might want to use for the impeller. So do we need to carry out a new set of experiments and devise a new correlation for each geometry? This is a very good question that we will try to answer today. So in my talk today, I'll be discussing the unresolved CFD-DEM model that our group has developed for solid liquid mixing. I will just briefly do an overview of the validation campaign and point you to the right references where we've carried them out. And we will investigate the influence of the agitator on suspension dynamics through various quantities, such as the fraction of suspended solid, concentration profiles, cloud height, and the RST. What is unresolved CFD-DEM? It combines CFD for the liquid with DEM for the solid. And we track the position and the velocity of each particles. The particle and particle geometry collisions are handled using simple contact laws, as in the case of the discrete element method. And the coupling between the fluid and the particles is carried out using expressions for the hydrodynamic forces. So it is a two-way coupling in the sense that the particle influences the motion of the fluid and the fluid influences the motion of the particles. What are the equations underlying this model? So for the fluid phase, we have the volume average Navier-Stokes equation, which in the present work we will be solving in their A form. So these are the volume average Navier-Stokes equation. The key difference here is that we are introducing a parameter, epsilon f, which describes the spatial variation of the void fraction. So it means that the velocity profile can be non-divergence free, because if we have a spatially varying void fraction, what we will have is that the divergence of epsilon f times u will be 0, if the flow is steady state. For the particles, we use Newton's second law, and the core of the DEM is the term highlighted in red, which is the contact forces. So by allowing overlap between the particles, we will model particle-particle contacts. And finally, we have the solid-fluid coupling, which are the hydrodynamic forces that we decide to apply on the particles. And in this case, we'll be considering pressure gradient, drag, and the viscous stress, which were all identified in our previous work to be the key dominant solid-liquid forces. So when we talk about mixing, we talk about two key elements, which is the presence of a rotating geometry. So in the past, our work concentrated on the use of immersed boundary to represent the impeller. You can see the work by myself and co-authors in the last 4 years. But one of the key issues with the immersed boundary approach we developed back then is that it was only, let's say, well developed for small rotating geometries for which the swept volume was small. When we look at the impellers we use in the laminar regime, they sweep a much larger fluid volume, as we can see in the figure here at the right with the helical ribbon. So clearly, in this case, it's more appropriate to use a method that is well posed, let's say, for thin geometries for which the swept volume is very large. And for this, we introduce a new approach using a rotating frame of reference in which we simulate the mixing in the rotating frame, so the Lagrangian frame. What does it look like? Well, if we look, let's say, at an helical ribbon, in the lab frame, what we would see is the helical ribbon rotating. In our case, what we will be doing is we will be simulating on top of the impeller geometry, putting ourselves in a rotating frame, and as such, the impeller won't be moving. This way, we can actually use an exact description of the geometry and use a conformal mesh. This could also have been done using a sliding mesh approach, but the issue here is that the sliding mesh interface would be so small in the narrow gap between the impeller and the outer wall that this generally leads to very large error in the pressure interpolation. So we use a rotating frame approach. So I'll just briefly discuss what we've done in the past in terms of model validation. So most of our efforts have been carried out in the laminar regime of operation for pitch blade turbines, and we compared in this work, in a past work, for example, the fraction of suspended solid as obtained through CFD-DM with what we could measure in our lab using the pressure gauge technique. And in this case, for a pretty large mass fraction of particles, so 10%, we were able to predict the just suspended speed with remarkable accuracy. And especially we were able to also predict the partially suspended state. So we could actually predict not only the speed at which all the particles were suspended, but also what fraction of particle we were suspending at various impeller speed. So I've added two references here on past papers we published 4 years ago and an article we published just a few months ago, where we did this validation for the immersed boundary approach, but also where we did it for the rotating frame approach. And in both scenarios, the model is able to capture the fraction of suspended particle with remarkable accuracy, which I think is a very strong improvement over the current state of the art. So now that we have this validated CFD-DM model, let's try to use it and do some engineering with it. So we'll use it to compare the performance of various viscous mixers. So there are actually a wide range of geometries which are used in the laminar regime. We have A, B, C, D, E at the right, which are different impellers that are generally used. A is going to be the anchor, B is going to be the helical ribbon, C is the paravisc, and D is going to be the max blend. And E shall be our reference, which will be the pitch blade turbine. So as we can see at the right, we see the actual velocity profile on various planes. So here we have the actual velocity as the color, and we have the streamlines in the plane. And we see that actually each configuration generates significantly different flow patterns. So the pitch blade turbine has two strong recirculating regions, whereas if you look at, for example, at the helical ribbon or the paravisc, the flow patterns that are generated are much more complex, but also they are, let's say, much more extended throughout the vessel. Whereas, for example, in the anchor, the middle portion of the vessel is barely steered or it's barely moved. So each configuration generates different flow patterns, and the question we ask ourselves is which one is the most efficient for solid liquid mixing in the laminar regime? So the first thing we looked at is the single phase power consumption, and we see that at low Reynolds number, the PBT really has a significantly lower KP, but the other agitators, they are very similar. So clearly we are comparing apples with apples here when we're considering all of these four closed clearance impellers. So the first thing we will look at is the fraction of suspended particles. So the pitch blade turbine requires significantly higher impeller speed to suspend the particles, as we can see at the figure here at the right. And this is pretty much normal, right? And because this is an unfair comparison, the PBT we're considering here has a much smaller diameter. So it's normal it requires a much higher agitation speed. So for the rest of this work, we'll only be looking at the agitated power. If we look at the power consumption, we see that most impellers actually perform quite similarly. The max blend and the anchor seem to be slightly better. That means that they reach a higher fraction of suspended particles at the lower power consumption. And by far, the helical ribbon is a clear outlier. It is by far the worst agitator amongst all. And it clearly requires a lot more power to reach close to full suspension. I mean, about, let's say, 3 to 4 times more power. So first question we should ask ourselves is why is the anchor and the max blend so much better, I guess, than the other agitators? And it seems that it is really related to the shear stress that is generated at the bottom of the vessel, and this strongly correlates with the capacity of an impeller to suspend. So here, if we look at the shear stress generated at the bottom for the anchor and the max blend, you see that in the same scale, they generate significantly higher shear stresses at the bottom of the vessel, and this in turn seems to be responsible for the higher degree of suspension that is reached. But a question we should ask ourselves is the fraction of suspended particle all there is to it? And that's not the case. We want to know, do these impellers reach the same solid concentration patterns? Do they reach the same cloud height? And do they have the same distribution of the particle throughout the vessel? And these are questions we will answer in the following slides. First, when we look at the void fraction, if we look at a velocity of n equal to ngs, or n higher than ngs, we see that actually the anchor is remarkably incapable of suspending the particles. So what I mean by suspending the particle here is actually distributing the particles. So while the anchor can lift all of the particles from the bottom of the vessel, it is incapable of putting particles in the upper region of the vessel. If we look at the ribbon, it takes significantly more time to suspend the particle, but as they are suspended and as n increases above ngs, we see that they become quite homogeneously distributed. In the case of the paravisc, it is very similar. The paravisc generates good axial flow and is very nicely able to suspend the particle and distribute them. And finally, the max blend has, let's say, a compromised behavior. At NGS, the particles are mostly located at the bottom of the vessel, and it is only with increasing the velocity even more that we're able to distribute the particle efficiently. So clearly, although the anchor appears to be a very good candidate, when we look at the void fraction distribution or the solid fraction distribution, it clearly is not that much of a good candidate. So when we look at the cloud height, as we see at the figure here on the right, so the cloud height normalized by the height of the impeller, the vessel, we see that actually the max blend and the paravisc are very good in terms of obtaining high cloud height. And the PBT is actually surprisingly good also. Once the particles are suspended, they go quite high. But if we look at the anchor here, we see that it requires significantly higher power consumption to reach the same cloud height. And this is not surprising because the anchor generates very poor axial flow. So it needs to compensate and needs to go to much higher impeller velocity to generate significantly higher axial flow. So here, even though the anchor appeared to be very nice from a suspended fraction point of view, it is very poor from a cloud height point of view. And the cloud height is a very nice concept to look at, and I think we have Professor Cresta to thank for that. It's a very nice concept that enables to see, well, actually, not only do we need to suspend the particle, but looking at which height we reach in the vessel is also very important, because we don't want to have a region where the liquid is not interacting with the fluid. The fluid is not interacting with the solid, sorry. So we can also look at the RSD, so a measure of the homogeneity of the distribution of the particle. And here we see that the paravisc is actually a very good impeller for that. At low power consumption, we reach very low RSD, and then the max blend becomes quite efficient. And then we actually reach a point where both the ribbon and the PBT are pretty efficient. But here the anchor is again the worst impeller. So the paravisc and the max blend, they offer quite good RSD at very low power consumption. So this enables us to draw final conclusions. Unresolved CFD-DM, as we've been using in our group, can be used to predict solid-liquid mixing. It can predict the fraction of suspended particle, but also the solid distribution and the cloud height, but also the RSD. Viscous solid-liquid mixing requires two elements: shear forces on the particle bed to suspend the particles, and strong axial circulation to lift the particles so that they can reach a high cloud height. Agitators that provide both of these perform extremely well. The paravisc and the max blend, maybe to a lesser extent in the case of the RSD. The PBT, actually the pitch base turbine, is actually a pretty decent agitator for viscous fluid, and for me this was a surprising thing. Initially I thought, well, these closed clearance impellers are going to be much better than the PBT, but it turns out that not necessarily. I would like to thank you all for your time. I will be glad to answer any questions, and I am always available to be reached by email if you have any questions or if you wish to discuss this work furthermore. So this work was in a large part carried out by master student Bastien Delacroix, who worked on this in the last 2 years, and a very young, talented individual who accomplished great work. And we have a third paper on this theme coming up. But I've added at the bottom here a list of all the references which are related to the work we presented today. And it's been a long series of articles in which we've worked both in terms of model development, verification, experimental validation, experimental investigation, but also numerical investigation. So I thank you all for your time, and I wish you the best at this conference.